Heat exchangers are devices that provide the transfer of thermal energy between two or more fluids at different temperatures. Shell and tube heat exchangers are the most widely used industrially due to their high efficiency and low cost of construction. The heat exchange occurs thanks to two important phenomena, conduction and convection. Due to its importance in the industry, it is necessary to model and analyze the behavior and performance of heat exchangers at different operating conditions. The use of computational fluid dynamics (CFD) has taken a very important role in the study of fluid mechanics since it allows the modeling of transport phenomena. The main objective of this project is to characterize a shell and tube heat exchanger computationally in order to determine the overall heat transfer coefficient for countercurrent and parallel flow, and also compare the results obtained in the CFD simulation and the CACAC and LMTD method.
For the selection of the meshing models, polyhedral cells were used in order to make a good discretization of the control volume obtained. Additionally, the prism layer model was chosen to obtain a good transition from the turbulent zones to the laminar zones near the walls. On the other hand, the surface remesher was used to obtain a mesh that would meet a high cell quality and improve those axes or corners that generate discontinuous figures when the CAD is imported into the program *CCM+, and finally the embedded thin mesher is used for the thin regions that are surrounded by fluid. It assumes that the thin geometries are entirely contained within another region. The mesh resulted in about 1.2 million cells with an average quality of 0.61 with the following attributes shown on the screen.
CACAC method was used to determine the force convection correlations for the fluids inside the exchanger. From Reynolds number, it was found that cold fluid in the exchanger has a laminar regimen because the viscosity of the flow depends on the temperature. The following correlation result number was used. However, the Reynolds number for the hot fluid is in a transition flow regimen in which the nacelle correlation is calculated by an average between both laminar and turbulent values of nacelle number. The following expression of nacelle number was used. This expression suggests that the effect of the thermal boundary conditions is almost insignificant.
These are the results obtained with the CACAC method. Parallel flow, as heat is transferred from the fluid with greater temperature towards the lower temperature fluid, the temperature of the fluids approach each other. While one decreases its temperature, the other increases it, trying to reach thermal equilibrium between them. It must be clear that the fluid with the lowest temperature never reaches the temperature of the hottest one. In contrast to the parallel flow heat exchanger, the concurrent flow heat exchanger might have the highest temperature in the cold fluid and the lowest temperature in the hot fluid after heat transfer ends in the exchanger.
Due to the calculus of Nusselt number shows higher values for the cold fluid compared with the hot fluid, the convective heat transfer along the heat exchanger is greater in the shell than in the tubes. As a result, convective heat transfer coefficients will be way too greater for the cold fluid. The velocity profiles obtained from the simulation in the *CCM+ software are detailed with the figures shown on the screen. It can be seen that these profiles remain relatively constant at different operating temperatures. The global heat transfer coefficients values obtained by the three calculated methods have the same magnitude order, which means that results are consistent with each other. Additionally, results expose that heat transfer coefficients values obtained with LMTD method have a 33% of difference from CFD values, while heat transfer coefficients obtained using CACAC method reached almost 68% difference from CFD values. This discrepancy might be due to all the three methods, where a distinct temperature difference along the heat exchanger is considered. CACAC method assumes a linear relation between inlet and outlet temperatures by averaging the two values. However, LMTD method establishes a logarithmic relationship between inlet and outlet temperatures.
The calculated heat must be the same for the cold steam as for the hot steam but negative. This is because the heat exchanger has an adiabatic behavior. The total heat transfer must be higher for a countercurrent flow. This is explained through the energy balance equation in which, as being the outlet cold temperature bigger in this kind of exchanger than in parallel flow, gets a higher Q.
Finally, our conclusions are that highest temperatures in the cold fluid are reached with the countercurrent exchanger. Convective heat transfer is greater in the shell zone of the exchanger compared with the tubes. The design for the exchanger which offers a better heat flow is the countercurrent. The heat exchanger has minimal dimensions. Therefore, it's way too difficult to notice turbulent behaviors or significant changes in temperature.